Hello everyone. We are pleased to present our ICCV paper, PoinTr, Diverse Point Cloud Completion with Geometry-Aware Transformers. In this work, we present a new transformer-based model for point cloud completion. Point clouds captured in real-world applications are often incomplete due to the limited sensor resolution, single viewpoint, and occlusion. Therefore, recovering the complete point clouds from partial ones becomes an indispensable task in many practical applications. Taking the incomplete point clouds as inputs, this task requires the model to predict the missing part. Point clouds in synthetic datasets like ShapeNet are always complete, while we can only obtain the incomplete point clouds in real-world scenes. Point cloud completion is the key to bridge the gap between researches on the synthesis data and real-world applications. Existing point cloud completion datasets like PCN usually consider objects from 8 categories, which is less diverse compared to the real-world scenarios. In this paper, we design a new and more challenging setting of point cloud completion containing more diverse situations that can better reflect the real-world scenarios. Our new benchmark, named the ShapeNet 5534 benchmark, contains more diverse tasks, more diverse categories, more diverse viewpoints, and more diverse levels of incompleteness. We also propose to test the model's generalization ability on objects from unseen categories. We propose a new transformer-based model to tackle the point cloud completion problem, where we reformulate the completion as a set-to-set translation problem. Our model, named PoinTr, is characterized by 5 key components: an encoder-decoder architecture to convert point cloud completion as a set-to-set translation problem, point proxies to represent the original point clouds as a set of feature vectors, geometry-aware transformer block to facilitate transformers to better leverage the inductive bias about 3D geometric structures, query generator to dynamically generate queries for the decoder, and a multi-scale point cloud generation process to generate final prediction in a coarse-to-fine manner. The primary goal of our method is to leverage the impressive sequence-to-sequence generation ability of transformer architecture for point cloud completion tasks. The recent success in NLP tasks like text translation and question answering has demonstrated the effectiveness of transformers to solve this kind of problem. Therefore, we propose to adopt a transformer-based encoder-decoder architecture to solve the point cloud completion problem. This is the detailed architecture of the encoder-decoder model. The encoder-decoder architecture consists of n multi-head self-attention layers in the encoder and decoder. The self-attention layer in the encoder first updates proxy features with both long-range and short-range information. Then a feed-forward network further updates the proxy features with an MLP architecture. The decoder utilizes self-attention and cross-attention mechanisms to learn structural knowledge. The self-attention layer enhances the local features with global information, while the cross-attention layer explores the relationship between queries and outputs of the encoder. The transformers in NLP takes as input a 1D sequence of word embeddings. To make 3D point clouds suitable for transformers, the first step is to convert the point cloud to a sequence of vectors. There are 3 steps to extract point proxies. We first sample a set of local centers using furthest point sampling. Then, we use a lightweight DGCNN with hierarchical downsampling to extract the feature of the centers from the input. Lastly, we add positional embeddings to local features. One of the key challenges of applying transformers is the self-attention mechanism in transformers lacks some inductive biases that explicitly model the structures of the point cloud. To facilitate transformers to better leverage the inductive bias about 3D geometric structures of point clouds, we design a geometry-aware block that models the geometric relations, which can be a plug-and-play module to incorporate with the attention blocks in any transformer architecture. To predict the point proxies of the missing parts, we propose to use dynamic query embeddings, which makes our decoder more flexible and adjustable for different types of objects and their missing information. We also propose a multi-scale point cloud generation framework to recover missing point clouds at full resolution in a coarse-to-fine manner. On the new ShapeNet 5534 benchmark, our method achieves over 44.7% improvement compared to previous state-of-the-art GRNet. We see our model works well on both seen and unseen categories. Our method also establishes the new state-of-the-art on the PCN benchmark. We conducted an ablation study to verify the effectiveness of our designs. We also set the new state-of-the-art on the Kitty dataset. Here are some visual results on the Kitty dataset. Our method can recover the complete point cloud of a car with more accurate boundaries and details like the tires of cars. Here are the qualitative results of the objects from novel categories. We see our model has better generalization ability compared to previous methods. Here are more qualitative results on ShapeNet and Kitty. Thanks for watching. Code and pre-trained models are available at GitHub.